Hello, welcome to this brand new video tutorial series on Intel microprocessors. This series is not gonna be very long. Basically, I'll start talking about the 8085 MUPI and then move on to the microcontroller like 8051. The tutorial is gonna be very helpful the night before your semester exam, and of course, if you have got some patience, I assure you that you are gonna love this subject right after you are finished. So hang on till the end, and I really encourage you taking notes while watching the lecture. And obviously I'm gonna have everything you are gonna need for revision like diagrams or code samples below. Check that out too. So without further delay, let's get started. In this session, we are gonna look at the basics of microprocessor. Now first of all, let's be very clear about it. Where we require a MUPI, let's call it MUPI for simplicity. We require a MUPI wherever we need programming. So you see in your mobile phone or remote controller or AC, and obviously your computer have a processor. Why? Because when you press certain buttons, certain things happen, right? So someone has to tell the device what to do when a specific button is pressed. Who is that someone? Right, it's your MUPI. Okay, now let's see the overview of a computer system. Here is your MUPI, then memory and the IO section, and here are the buses. To be brief, what are buses? They're simply connectors. We shall talk more about buses later. Before that, let's see each of these components individually. Let's start talking about memory. Now, what comes first to your mind after you hear the term computer memory? Yes, RAM-ROM is fine, but what they basically are? To have this answer, you need to know what you store in the memory. Do you store a song, an image, or a data file? Actually, none of them. What you store is zeros and ones. In other words, you store bits in the memory. A song in your computer isn't stored as a song. It's a sequence of zeros and ones. So is it clear now? Forget about memory. From basic electronics knowledge, try to answer this simple question. How do you store a bit? Right. It's a flip-flop. It's a simple D flip-flop. And it's very interesting. Say you have sent a clock pulse and have made the D bit high, that is 1. So Q becomes 1, 2. Now make the clock low and make D 0, 1, whatever. It's not gonna change. It's latched. So you see, flip-flops are ideal memory elements. Now you want to store many millions of bits in memory. So you need many flip-flops. But how many exactly? Always keep in mind that there are millions of different memory locations in computer memory, and each location stores 8-bit or 1 byte of information. I repeat, each location stores 8 bits or 1 byte of information. So how many flip-flops are required in each location? Right, definitely 8 is required. So you see. So as a whole, what do you store in memory? Files. They can be both program files or data files. What are program files? They are nothing but instructions. Now coming back to our processor. So our processor or MUPI controls the access to the memory through the buses. Say when you want to execute a program which is already stored in the memory. So actually what happens is the instruction in the form of zeros and ones come one by one to the MUPI. This process is called fetching. Then what? Execution. No, my friend. MUPI has to first decode the instruction. Now very briefly, let's see the process of decoding. Here you can see a 2 to 4 decoder. So for each combination of zeros and ones, you get different outputs high. That is the point of decoding. For your information, these instructions in the form of zeros and ones, that you may call machine language also, are basically called an opcode. What? An opcode. So when an opcode comes to the MUPI, it decodes the opcode. It means the microprocessor, of course, the microprocessor decodes the opcode. Now referring to this particular decoder, say if Q0 is high, it triggers the adder in the ALU, that is your arithmetic and logic unit in the CPU. So when 00 comes to the decoder, MUPI knows it has to add two numbers. Say the instruction was add B. It's an assembly language instruction. After your assembler assembles this instruction, 00 gets stored in the memory because that was the particular opcode for add B, say for example. Now this 00 is your opcode. Now when you execute it, come on, you already know it, repeat after me. The opcode is fetched, then yes, decoded, and then MUPI executes the command. Clear? Now there is a very relevant question, why we use a hexadecimal system for computers. There should be some valid reasons behind it. To understand the reason, first of all, let's get this simple fact. How many total numbers you can represent when you have certain numbers of bit? When you have a single bit, you can have 0 or 1. Using 2 bits, you can have 2 raised to the power 2, that is 4 total combinations. They are represented as 0 to 3. Similarly, for 3 bits, you have 8 total combinations, that is 0 to 7. But you intend to use decimal system. So you have to represent 8 and 9 also. So you have to use 4 bits, this much is obvious. When moving to 4 total bits, you have 1000 for 8 and 1001 for 9. Now apparently the problem is solved. Say a situation comes when we have to add 1001, that is 9, and 0001, that is 1. In binary, you get a combination like 1010. In decimal, it is 10. So now do you get my point? You have no single digit representation of the combinations after 1001. That is why we had to introduce hexadecimal system. Now we have the rest of the combinations as well. Now the last topic. Let's talk about buses. You already know what they are. They are connectors, right? This is your overview. I keep referring to this as it is so simple but understandable at the same time. Now buses are used to send or receive zeros and ones. Now the sequence of zeros and ones can be an address or data or control signal, whatever. Here you can see a simplest representation of a bus. At one end there is a switch that connects the bus to ground. Now say you have to send a 0. Simply close the switch. Now it's connected to the ground. At the other end you get 0. Again when you need 1 at the other end, open it. By TTL logic, floating signifies high. So you see they are this simple. As you can see, there are 3 kinds of buses. Now let's understand them with a simple example. Say you want to read the data from a memory location 4000. What we have to give first? U means the MUPI. Right, the MUPI has to first send the address 4000H because it cannot work on some random address. It has to read from 4000 only. Now it's logged. This address is logged. Now tell, what after it? Data bus? No, my friend. MUPI has to tell whether it wants to read or write data. In this case, it has to read data. So through control bus, it will say it has to read the data. Only then the data 29 is gonna come to the MUPI through data bus. Are we clear? Now always keep in mind a fact that whenever data comes to the MUPI, it's reading. When MUPI gives data, it's writing. Okay, so this is reading, this is writing, this is reading, this is writing. Now one last thing. After this we are done for now. Size of the memory and size of the bus. Size of the bus means total number of lines. See, memory locations have to be all different, right? So when you have, say, 2 line, you have 2 raised to the power 2, that is 4 different combinations. Similarly, if you have 16 buses, you have 2 raised to the power 16 different combinations. 8085, for information, has 16-bit address bus, that is 16 different lines comprising the address bus. So it can afford 2 raised to the power 16 different memory locations. And previously I have told you that one memory location can have 1 byte. So total affordable memory for 8085 microprocessor is 2 raised to the power 16 bytes or 64 KB. I think this is it for now. Please like, share and subscribe if you wish. Thanks for watching. Bye.